So today we are going to discuss about the inertia forces acting on reciprocating parts. Okay, let us consider a slider crank mechanism. So this part is our slider. This is the fixed link. Then we have connecting rod, crank. Okay, let's say this is O, A, B. Now let us draw the crank circle. So the crank is fixed over here. Now let's say length of the crank is L as a reconnecting rod and length of crank is R. This part is inner dead center. This part is outer dead center. Now the angle induced by the connecting rod at this particular instance is beta, and the angle turned by the crank from the IDC is theta. Let's say this line length is y. Now initially when the crank was here at the IDC, that time the slider position was somewhere here. Okay, that the slider was here initially. Now let's say this is B1 position, and because of the rotation of theta rotation of the crank from IDC, the slider moved a horizontal distance through X, we can say. Okay. Now, if at all you are interested for the velocity and acceleration, of piston, then we can derive that. So for this, let's your L, as I told, is the length of connecting rod. R is the length of crank. X is the displacement of piston. Displacement of piston from the inner dead center IDC when the crank turn through an angle theta from IDC. Okay. Now we have this length X is equal to B1 B, or I can say this is equal to B1 O minus of BO. Okay. So when the crank was at 0 degree, that time B1 O will be equal to length of the connecting rod plus the length of the crank. So L plus R minus this BO we can segregate as, let's say this point is A1. So this will be equal to BA1 plus A1O. So further we can write this as L plus R minus of your L cos beta plus R cos theta. Okay, you can write in this way. Now we have this x is equal to nr plus r minus nr cos beta plus r cos theta if we choose a ratio L by R is equal to N, such that this L can be represented as NR. Okay, so now X will be equal to, you take this R out, so we'll have N plus 1 minus your N cos beta plus cos theta. Okay, now let's say this is equation 1. Now cos beta is equal to 1 minus sine square beta. Okay, which from the geometry we can say it is 1 minus y square by L square. Here if you look at the geometry, so this sine beta will be y by L, so sine square beta will be y square by L square. Okay, so instead of this y we can write 1 minus, it is r sine theta square divided by L square whole root over. Okay, because here you can see this y is also equal to r sine theta. Okay, so this way also we can write. Now we can write this equation as in the numerator will have sine square theta divided by L square. When you bring down this r square to the denominator, it will be L square by r square, which is equal to n square. Okay, so upon simplification we can write that cos beta is equal to 1 by n root over of n square minus sine square theta. Okay, so we can express in this way. Let's say this is equation 2. Now substituting this value of cos beta, substituting the value of cos beta in equation 1, we can express this x as r into n plus 1, okay, minus of n cos beta plus cos theta, or we can write this as r into n plus 1 minus your n square minus sine square theta plus cos theta, substituting the value of cos beta. So we can write this equation as r into 1 minus cos theta plus n minus of root over of n square minus sine square theta. Okay, let's say this is equation 3. Now if the connecting rod is very large compared to the crank length, this n square will be large and maximum value of this sine square theta will be 1. Okay, not equivalent, it is equal to 1. So then this root over of n square minus sine square theta can be represented as root over of n square, or we can say it is equal to n. So equation 3 can be represented as this x is equal to r into 1 minus cos theta, because n and this here instead of this we are writing n, so they will get cancelled out. So finally we will have x equal to 1 minus r into 1 minus cos theta. Okay, let's say this is equation 4. Now this equation 4 holds good for SHM. Okay, so thus piston executes a SHM when connecting rod is large. Okay, now if we are interested to find out the velocity of piston, so velocity of piston, let's say find out this velocity of piston, which is denoted by V subscript P. Okay, this velocity of piston Bp will be equal to dx by dt. So in terms of crank angle, dx by d theta into d theta by dt. So we can write this Bp will be equal to d by d theta of x into 1 minus cos theta, okay, plus n minus n square minus your sine square theta to the power half, okay, into d theta by dt. Okay, or we can write this as your r, sorry, here it is r. So r into 0 plus sine theta, 0 plus sine theta plus 0 minus half n square minus sine square theta to the power minus half, okay, into 2 sine theta cos theta bracket close. So this d theta by dt can be represented as omega. So we have r omega of sine theta plus sine 2 theta, okay, divided by 2 root over of n square minus sine square theta. So this is equation 5. So this equation gives us the velocity of piston. This is velocity of piston. Now next, here we can have certain assumptions that if your n square is large compared to sine 2 theta, this Bp will be equal to r omega sine theta plus sine 2 theta by 2n. Okay, let's say this is 6. If sine 2 theta by 2n can be neglected when n is quite large, then in that case Bp will be r omega sine theta. So depending upon the condition we can use the equation. So this is equation 7. Now let us find out the acceleration of the piston. Acceleration of piston. Now acceleration of piston can be denoted by symbol A subscript P. So this AP will be equal to dV by dt, and in terms of the angle, let's say dV by d theta into d theta by dt. Okay, so we can represent this AP as this AP is equal to d by d theta of r omega into sine theta plus sine 2 theta by 2n, okay, into omega. D theta by theta is omega. So we have this acceleration of piston is expressed as r omega square, okay, r omega square cos theta plus cos 2 theta by n. So this equation gives us the acceleration of piston. Let's say this is equation 8. Okay, equation 8. Now here also there are certain assumptions that if your n is very large, then acceleration of piston AP will be r omega square cos theta. Okay, this one is 9, and when theta is 0 degree, that is at the inner dead center, acceleration of piston is omega square, you can say r omega square, okay, 1 plus 1 by n. Let's say this is 10, and when theta is at 180 degree, that is at ODC, outer dead center, acceleration of piston will be r omega square minus 1 plus 1 by n. Okay, equation 11. And at theta is equal to 180 degree, when the direction of rotation is reversed, so AP is equal to r omega square 1 minus 1 by n. This is equation 12. These are the conditions, okay, that can be applied as and required. Okay. Now coming to the angular velocity and acceleration of connecting rod. So you can write, we have this y from the initial geometry. I can say y is equal to L sin beta, okay, which is also equal to r sin theta. So I can write sin beta is equal to sin theta by n. This is a relation between sin beta and sin theta, okay, because L by R is equal to n. Let's say this is equation 13. Okay, now differentiating with respect to time, we can say it will be equal to cos beta d beta by dt is equal to 1 by n cos theta d theta by dt. Okay, or we can have d beta by dt is equal to cos theta divided by n cos beta into omega. Okay, or we can write that omega of the connecting rod, angular velocity of connecting rod, is equal to omega times cos theta divided by n into, now you substitute the value of cos beta here, so you'll have 1 by n root over of n square minus sin square theta. Okay, so this is the relation to find out the angular velocity of connecting rod, omega c. Okay, let's say this is 14, or this omega c can be further simplified as omega c is equal to omega times cos theta divided by root over of n square minus sin square theta. Okay, let's say this is the equation, final equation. So this is equation 14. Okay, now let alpha c is the angular acceleration of connecting rod. Okay, so we can write here that d omega c by dt is equal to d omega c by d theta into d theta by dt. Okay, so this will be equal to omega times dy d theta of cos theta into n square minus sin square theta minus half, okay, into omega instead of d theta by dt, or we can write this as omega square minus cos theta into half of n square minus sin square theta minus 3 by 2 to the power minus 3 by 2 into minus 2 sin theta cos theta. Okay, no, further plus n square minus sin square theta, okay, minus half into minus sin theta. Okay, now bracket close. So upon simplification we can write this as omega square, bring sin theta out, so we'll have cos square theta minus n square minus sin square theta, okay, divided by n square minus sin square theta to the power 3 by 2. Okay, or we can write this as minus omega square sin theta of n square minus 1 divided by n square minus sin square theta to the power 3 by 2. Okay, so this is the final equation for the acceleration of connecting rod. Let's say this is equation 15. Now this negative sign, star mark, negative sign indicates that the sense of angular acceleration of the connecting rod is such that it tends to reduce the angle beta. So in this case angular acceleration is angular acceleration is clockwise. Okay. Now, what are the different forces acting on the engine? So, heading will be engine force analysis. Engine force analysis. Okay. Now, in a broader sense, if we say, let me draw the schematic of the engine. Let's say this is my cylinder, which we earlier used to call the slider. Okay. The cylinder will have a piston inside and a piston rod, and this is connected with the connecting rod, and connecting rod is connected to the crank. Okay, so let us mark all the points on it. So this is O, A, B, usual. Now the different forces acting on it can be marked as, first, a force acting in the cylinder is denoted by F here, okay, which is the uh, piston effort. We can say this F is piston effort. Then we'll have a force along the connecting rod, okay, here. All these forces we'll discuss. This is denoted by Fc. Then we have a thrust on the side of the cylinder, okay, let's say Fn, okay, thrust on the side of the cylinder. Then we have a crank effort, okay, crank effort, which is normal to the crank. So let's draw it. So it is denoted by F subscript T, okay, known as crank effort. Then we have the thrust and the bearing, okay, it is denoted by force Fr. If you produce the crank, you will find out the direction Fr. So these 5 forces are the basic forces acting on the engine, whose magnitude we are going to derive. Okay. Uh, as usual, this angle is your beta, this angle is theta. Okay. Now, in this process, let us first find out the piston effort. First force is piston effort, denoted by symbol capital F. Okay, capital F. Now, let this piston effort is defined as piston effort is defined as the net force applied on the piston. Okay. Let A1 is the area of cover, and A2 is the area of piston rod end, area of piston rod end, and P1, small P1 is the pressure on the cover end, pressure on the cover end, small P2 the pressure on the rod end, pressure on the rod end, and mass M is the mass of reciprocating parts. Reciprocating parts. Okay. Now the pressure. What is cover end and piston end? Let me describe you. Let's say this. If this is our horizontal cylinder. Okay. So let's say this is cylinder. Then this one is our piston, and this is piston rod. Let us hatch this portion. Okay. So this part is our cover end, and this part is our piston rod end. Piston rod end. Now this area is A1, which is of course pi capital D square by 4 if D is the diameter. Okay, if D is the diameter, and let's say if small d is the diameter of piston rod, then this area A2 will be pi by 4 your d minus d square. Okay, so this is the cover end and piston rod end. Now let's say pressure on piston due to gas pressure denoted by Fp is equal to P1 A1 minus P2 A2. Okay, say this is equation 1. Okay. Now inertia force denoted by symbol Fb will be equal to mass into acceleration of piston. So we can represent this as m r omega square cos theta plus cos 2 theta by n. Okay. This is denoted by equation 2. This Fb equation 2. Now inertia force acts always opposite to the acceleration of piston. This inertia force always acts opposite to the direction of acceleration of piston of piston. So the net force on piston F is equal to your FP, force due to gas pressure, minus the inertia force FB. Okay, let's say this is equation 3. Now, in case of frictional resistance, in case of presence of any frictional resistance denoted by symbol capital F subscript F, okay, this net force will be net force F will be equal to force due to gas pressure minus the inertia force minus the frictional force. Okay, so this will be your equation 4. Now, in case of vertical engine, weight of piston or reciprocating parts, you can say reciprocating weight of the piston or weight of the reciprocating part is also considered. So in that case, the net force F will be equal to force due to gas pressure plus the weight, that is mg, minus of the inertia force Fb minus of the frictional force Ff. Okay, let's say this is equation 5. So as and when required, we'll be using this equation 3, 4 and 5. Okay, now second force is the force along the connecting rod, which was Fc, force along the connecting rod. Now let this, if you resolve it from the geometry, you'll see this Fc into cos beta will be equal to F. Okay, so this Fc will be F by cos beta. Okay, question 6. Now third force is the thrust on the sides of cylinder denoted by F subscript N. Okay, so if you resolve all the forces, you will see this Fn is basically equal to Fc of sine beta. Okay, or you can say F by cos beta into sine beta, or you can say this Fn is equal to f of tan beta. Okay, equation 7. Now fourth force is crank effort. Crank effort. This is denoted by symbol F subscript T. Okay. Now Ft is the crank effort. This crank effort is the net force on the crank pin perpendicular to the crank length which gives required turning moment on crankshaft. Okay, so Ft, so now taking moment about that point O, we can say Ft into R is equal to basically Fc into R sine theta plus beta, or you can say this Ft is equal to F by cos beta into sine theta plus beta. Okay, this is equation 8. Now fifth one is the thrust and the bearing. This is denoted by symbol F subscript R. Okay, so this Fr is basically Fc cos theta plus beta, or you can say this Fr is equal to F by cos beta into cos theta plus beta. Okay, this is equation 9. Now how we are getting this theta plus beta? Let us go to the geometry. Here it will be clear. If you see here, we have this Ft is normal to OA, right? Now what about let us produce this line, connecting rod line. Okay, so if this angle is beta and this angle is theta, what about this angle? This will be equal to theta plus beta, isn't it? So you drop a normal to the horizontal dotted line. This will be like this, and if you drop a normal to this AB, let me show a different color. Let's say this line, which is normal to the extension line. So this will be equal to your R sine theta plus beta. Okay, and this will be equal to r cos theta plus beta, right? And if we know that this angle is beta, so if you draw a normal to this line OB, let me show another color here. Let's say if you draw a line normal to this horizontal line OB, let's say like this. So this angle, okay, this angle will be beta. So this is the basic geometry. So we can find out all the associated force in this way. Now last one is, suppose we are interested to find out the turning moment, how much turning moment is acting on the crankshaft. The turning moment on crankshaft. Okay. Now turning moment is denoted by symbol capital T. So this T, as I told, it will be equal to the force Ft, that is the crank effort, okay, multiply with the crank length R, okay, and we have value of Ft is equal to F by cos beta into sine theta plus beta multiply with R. Okay, you can write in this way, or we can say that this is equal to Fr F dot R cos beta into sine theta into cos beta plus cos theta into sin beta. Okay, or I can write this as F dot R, okay, into sin theta plus cos theta sin beta into 1 by cos beta, multiplying 1 by cos beta with every element. Okay, or I can write this equation as F dot R, okay, sin theta plus cos theta into, substituting sin beta in terms of sin theta, I can write here as sin theta by n multiply with, now substitute the value of cos beta, so we'll have 1 by n times root over of n square minus sin square theta here. Okay, so it will be equal to F dot R into sin theta plus 2 sin theta cos theta 2 sin theta cos theta divided by 2 into, I can write 2 into root over of n square minus sin square theta. Okay, so this is the turning moment. So this is equation 10. Also, we can represent this T as simply Ft into R. R, this is F by cos beta into R sin theta plus beta. Okay, so this T can also be represented as the force acting, net force acting in the cylinder F into OD. Remember, this is also, and this also will give you the same result. Now, what is OD? OD is the uh, this line. Let me show you. If you take this point as D, the normal on the horizontal axis line. Okay, because this is normal to this line. So this force F multiplied with this distance OD will also give you the turning moment acting on the crankshaft. But normally we take this as Ft into R. Okay.